Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation about optimization using calculus. And I'm specifically choosing this example because it showcases the idea of choosing to optimize the square instead of optimizing the actual function. And before I even get into this example and start reading it out, let me just showcase what I mean by optimizing the square. So suppose that somebody comes in, they say, listen, you need to optimize y. Y is just equals some function of x, okay? And you need to maximize that. Well, that means you need to find, let's say on some interval a to b. Oops, that was supposed to be an a, but it looked like a g there. A to b. And you need to find the maximum of that function on the interval, or the minimum. Doesn't really matter to me. Well, it turns out that the maximum for this function will occur exactly where the maximum of the square of the function occurs. They actually have the same maximum. If you think about any function, as long as, by the way, the function's positive, okay? That is kind of important. So as long as our function is positive, so you have something above the x-axis here, it does something like this, whatever it is, right? If you square it, all the y values get squared, right? And so this y value, let's just pretend as though this height here, this is kind of an important point. Let's pretend that height is y equals 1, okay? That means that this y value becomes square. So it might be like, slightly larger. Oops. And this y value right here gets squared, so it becomes slightly larger. Think of a y value below 1, like a half. If you square that, it actually becomes smaller. Okay, so anything below 1 becomes a little bit smaller. Okay, so you have something that looks like this. Notice, by the way, where I'm crossing the line y equals 1 is exactly where my original function crossed the line y equals 1. That's because when you square 1, it still is 1. This is just a graphical representation of this, but notice if I want to find the maximum right here, let me highlight this, it would correspond to the same x value for the maximum right there. If I want to find the maximum right here, it would correspond to the same maximum right there. If I want to find the minimum, let me use a different color and zoom in because this is kind of hard to see. But if I want to find the minimum right here, it's the same as the minimum for the black function. If I want to find the minimum right here, again, the same for the black function. So it turns out that the minimums and maximums for the square of the function, as long as the function is positive, they occur at the same time as the minimums and maximums for the original function. Now I'm making this caveat where the function is positive because if a function is negative and you try to square it, it all of a sudden flips up to being positive and all bets are off. Okay, so it still does result in an optimization, just not a maximum necessarily or a minimum. Anyhow, so let me get back to my original view here and scroll over. There we go. And let's go ahead and see why I'm going to use the squaring function. So we have an 8-foot tall fence runs parallel to a quote-unquote tall building. It just means a building that's sufficiently tall to where we don't have to worry about the actual height of the building. Okay, and that fence, which is 8 feet tall, runs at a distance of 4 feet from the building. So as a side view, let me go ahead and draw in some ground here, and let me move. I have to move a couple things out of my way. So as a side view again, I'm going to draw the ground. So here's the ground. Well, I guess my ground is green. Didn't mean for that to be that way, but there it is. And let's go ahead and draw the wall of the house. So this time I'm not drawing with green. So there's my house. Okay. And then let's draw a fence 4 feet away from that. So the fence might look something like this. And the fence, by the way, is 8 feet tall. So maybe I should grab that guy and move him over here. Well, something like that. All right. So that fence is 8 feet tall. This distance here is 4 feet. And I want to slap a ladder on the other side of this fence, and ladder I'll put in black here, and I want it to reach the wall of the building. So there's my ladder. Obviously, there's a lot of different ways you can set this up, but I'm just visualizing it this way. You should note there is a right angle there and a right angle there. Okay. And the question is, what is the length of the shortest ladder that will reach from the ground over the fence and to the wall of the building? So I'm going to go ahead and call this length L, the whole entire ladder length L. And I am going to go ahead and set up a formula that helps me figure out the length of the ladder. Now, I need a master equation. I've read the problem. I've drawn a picture. Let me go ahead and let, even though I set it there, let L equal length of ladder. And what we need to do is optimize L. In other words, minimize L. So we need a formula that involves L. And I can see from the fact that we have this very large right triangle, specifically the one that I'm drawing in black here, that large right triangle, I can use Pythagorean theorem on. It has some height h, and it has some floor length, which I will call x. So one equation for this is L squared is equal to h squared plus x squared. And of course, if you've watched the video where I talk about the method of solving optimization problems, I had mentioned back then that you often get a relationship with too many variables. Notice there are 3 variables here. That's too many variables. So we need a relationship between h and x. Well, something else I need to showcase here. And I will draw this maybe in a different color. That triangle that you see there that I just drew in, make it a little bit bolder, is a similar triangle to the large triangle. Right? So our good old algebra skills come into play here. And so what I'm going to do is make a relationship between the side lengths of that triangle, the smaller triangle, and the side lengths of the larger triangle. Now, one thing I should mention here is this side length, well, it's almost the entire length x, but we've already taken 4 of it away, so it's x minus 4. Using similarity of triangles, I can tell you that x minus 4 is to side length 8. Let me highlight that. X over 4 is to side length 8, as x is to side length h. So as x is to side length h. And now I'll go ahead and solve this. It actually doesn't matter which one you solve for in this case. I'll solve it for h, just because there's only one h there. It's a little bit easier to solve for. So this will imply that capital H is equal to 8x over x minus 4. So that means that wherever I see an h in my equation, my master equation, which I should have written that in, that's the master equation, and this is the relating equation. Wherever I see an h in there, I'll replace it with 8x over x minus 4. So here I go. Let's do that. This will imply that L squared is equal to 64x squared over the quantity x minus 4 and quantity squared plus x squared. Now, here's where I'm going back to my statement about wanting to optimize the square. Remember, what I want to minimize here is the length of the ladder, right? But if I try to solve for L here, I'm going to get a square root. And that means I need to take a derivative of a square root function, and it just gets kind of messy. So instead, to avoid square roots, I'm just going to take the derivative implicitly as it's written, right? So I'm going to take the derivative of both sides with respect to x. If I do that, I will get 2L dL dx, or in other words, L prime, is equal to, and the derivative of the right-hand side, notice there's no radicals here, so that's kind of nice. Derivative of the right-hand side, well, that's a quotient rule, unfortunately, so that's 128 x times the quantity x minus 4 and quantity squared, minus that numerator, 64x squared, times the derivative of the denominator, which is 2 times x minus 4 to the first, times the derivative of x, but that's just 1, all over that denominator squared. So that's x minus 4 to the 4th, and then plus 2x. It still looks pretty terrible. However, at least we can kind of solve this out and not really sweat it too much. There's a little cleanup that you can do here. So remember what we need to do. We need to look at the critical numbers. And the critical numbers for this function L will occur when L prime is 0 or when L prime does not exist. Now, L prime does not exist when x is equal to 4. So I happen to know that I don't have L prime when x is 4, so I can avoid that. Also, L prime is equal to 0. Well, if you set L prime to equal 0, that means that this piece right here turns into 0. And so you end up getting that 0 is equal to, and now use some algebra from way back when, right? Both of these have 128 in it, which you can divide. Well, I'll just factor that. 128. They both have an x minus 4, which will cancel 1 power of x minus 4 downstairs. And so I have x times x minus 4 to the first instead. And I'm going to factor that 128 out. In fact, I can actually factor out an x out of there too. So 128x times the quantity x minus 4. Remember, I factored off a 128 and an x, so just minus x here, all over the x minus 4 being cubed now because I deleted off 1 power, plus 2x. That's not bad. And let's see what else we could do. You could multiply both sides by the LCD, or you could go ahead and solve this out. Actually, I'm going to do a little bit of extra cleanup here. 0 is equal to 128x times the negative 4 all over x minus 4 cubed plus 2x. That actually helps out that I've done that. I'm going to go ahead and add the first term to both sides. That's a negative 512. So positive 512x over x minus 4 cubed is equal to 2x. Now I'm going to do something I would normally tell my algebra students to never do. Remember what x is. X is that full length here, the full floor length of how far away the bottom of the ladder is from the wall. And so obviously x can never be 0. So because I know x is non-zero, I'm going to divide both sides of this by x, and actually by 2, just because I can, right? So you get 256 over the quantity x minus 4 and quantity cubed is equal to 1. Normally you cannot, it would be somewhat dangerous to divide by the variable x, but because I know it's non-zero, I can do that. And then finally multiply both sides by x minus 4 cubed. So you have 256 is equal to the quantity x minus 4 and quantity cubed. And then you take the cube root of both sides. And I happen to know, by the way, that 256 is 2 to the 8th. So when you take the cube root, you'll get 2 to the 8 thirds is equal to x minus 4. Or in other words, that x is equal to 4 plus 2 to the 8 thirds. And you can actually simplify that even further if you want to, but I think that's pretty good. Okay, so our critical points, right? Our critical numbers, just to reiterate, are 4 and, like I said, 4 plus 2 to the 8 thirds. Those are our two critical numbers. And then we also have to consider the domain of our function L to begin with here. So what can the ladder be? Well, technically speaking, the ladder could be a lot of lengths, right? It could be anything from, well, it can't be length 0, obviously, but there's a range of lengths it can be. I'm not going to check the ends of that. Obviously, if you let L go to infinity, then it's not the shortest ladder. And also, if you try to tilt this ladder up, let me get this here. If you try to tilt this ladder up, it'll also still go to infinity. So based on X, really the sweet spot for X, or for this distance, this floor distance, is going to be something greater than 4 and less than infinity. So I'm just going to go ahead and say the domain goes from, of our function L, goes from 4 to infinity. But at some point, it's going to be somewhat ridiculous to actually have it go to infinity. So anyhow, you can't check the endpoints of that. Critical numbers. So let's take a look at the values X versus L squared, right? It's our function's L squared, not L. So if you plug in 4 versus 4 plus 2 to the 8/3, you can't plug in 4 to our original function here because there's a domain error, so it does not exist. Okay. So we don't worry about that. And now we go ahead and worry about this guy right here. Okay. And by the way, I'm not testing L prime. There's only one spot on this function where you have a critical number like this, and that spot is going to be a minimum. So if you plug this into your function L squared there, it's going to be a bit of a mess, honestly. What is it? 64x squared over x minus 4. So 64 times this number squared over x minus, or yeah, this number minus 4. Is it squared though? Yeah, it's this number minus 4 squared. Well, if you take this number and subtract 4, it's just going to be 2 to the 8/3, but you're going to square that, so it's 2 to the 16/3. And then let's see what else is there to L squared plus x squared. Okay, plus this number squared. Okay, and so if you grab a calculator, I'm not sure if I have this pre-computed. Let me just double check. And I didn't, so I just went ahead and grabbed a calculator really quickly. This tells me that L squared, not L, not the ladder length itself. The length of the ladder is definitely not 277 feet. But if I take that length and square it, actually it should be square feet then, huh? Then you get 277 square feet. And then that will imply that L is approximately, if you take the square root of that, 16.6 feet. So you need at least a 16-foot or almost a 17-foot ladder. Let's use a little bit of a logic check here. I need a ladder to go over an 8-foot fence. It should make sense. That should at least be 8 feet plus the additional 4 feet that you need here. So that's at least 12 feet. But that's 12 feet if your ladder looks like a square, right? But it doesn't. It's a straight ladder, so you're going to need some type of extra length there. So it does make sense. It should be quite a bit greater than 12 feet. And I think that's pretty believable that it's around 16 to 17 feet. Again, this is a good example that you could have optimized the square root function if you wanted to, but there's really no need to. You can just stick with the square function and optimize that. And the beautiful thing about that is when you go to find the critical numbers, that derivative, you just go ahead and set equal to 0. Finally, some people will call me on this. They'll say, but wait a second, you didn't actually showcase this was the minimum. You just kind of waved your hands a little bit and said, oh, this is, I'm telling you this is the minimum, and you'll just have to believe me. Well, if you want to check that this is the actual minimum, you could create a number line for L squared. Okay, and remember, this is going to be, actually, I shouldn't say L squared. I should say create a number line for L prime. And remember that L prime is this guy right here. So you'd actually have to divide everything by 2L. Remember, 2L is just a positive number. So you'd be dividing by a positive number. So that honestly is not that big of a deal. Dividing by a positive will not change whether something's positive or negative. So ignore the division by this 2L on both sides. And what you can do is plug in that 4 plus 2 to the 8/3. You can figure out an approximation to that. And I'm just going to type that into my calculator really quickly. 4 plus 2 to the 8/3 power is approximately equal to 10.3. So if you roughly equal to 10.3. So if you plug in a number into L prime here, this guy, the right-hand side, if you will, if you plug in a number greater than 10.3, and you could choose any number you want. If you do that, let's go ahead and find out actually what it is, right? So plug in a number. Actually, in this case, I would probably plug in a large-ish number. We actually simplified that right-hand side quite a bit by getting to here. That is the simplified version of the right-hand side. So let me go ahead and say that this is equal to negative 512 x over x minus 4 cubed plus 2x. So it was just me simplifying that right-hand side. And the question is, when you have a number that's like larger than 10, let's say a billion or something like that, right? Then the numerator here will be negative. The denominator will be a billion minus 4 cubed, which is positive. So you have a big old negative number. Unfortunately, you have 2 billion. So maybe I shouldn't have chosen a billion. Just choose a number greater than 10 then. So let me just quickly compute like with 20. So if you actually do plug in about the number 20 into this right-hand side, it will be positive. So I'm going to go ahead and say that L prime is positive over here, which means it's increasing. The function L is. In fact, L squared is. And then let's plug in a number less than 10. Obviously, you want it to be greater than 4, though. So you can plug in a number like 5. So let me go ahead and do that. Actually, that I can do pretty quickly in my head, because if you plug in a 5, this numerator is like a negative 2,500. Denominators, I mean, it's not exactly, but it's close enough. And that denominator is going to be 1. So we have some very large negative number plus 10. Well, that's going to be negative. So I happen to know the derivative will be negative over here. So it's the function decreasing, then goes to increasing. So that is a local minimum. And that is actually the only minimum. So therefore, we have minimized the length of the ladder at that moment. That last little bit's just because some people might call me on that and say, well, you didn't actually show as a minimum. Anyhow, okay, so I hope this was a helpful video for you. I hope I didn't confuse you too much. And have a good day. Study calculus.